Hello and welcome. Today's lecture is on related rates of change, a new question I wrote for one of the synoptic papers that I've done recently. I can't remember whether it's on U, V or W. As you can see, it's 4-star, so it's actually very quick to do. But you just need to know how to approach it. So I'll read the question because my printer ate a bit of the left and a bit of the right. So what it's actually saying is a particle is moving on the curve with equation x, and let's start writing some stuff down. Let me just move that here so it should be able to see it still. So the curve that the particle is moving has equation x is equal to y cubed plus y plus 1, which immediately we have a problem because, of course, normally we have the curves in the form y is a function of x. Now we have it x a function of y. And its coordinates at time t are x, y. So all standard stuff at time t. So this is the trajectory of this particular object. When the y coordinate of the particle is 5, so when y is 5, let's write this down, the rate something dt at which the y coordinate is changing with respect to time. So when y is equal to 5, dy by dt is not dy by dx. The rate at which the y coordinate is changing with respect to time is a quarter. So you could have written that like this. That's how I normally write it, evaluated as 5. And what the question would have said there is find the rate at which the x coordinate is changing at that time. So we want dx by dt evaluated when the y coordinate is 5, at what rate now the x coordinate is changing. And let me just put the question again, but as I said, it's just chopped up a little bit of the edges, and you will find this in the synoptic papers, either U, V or W, and on the book Related Rates of Change. So let's put this in a little bubble. This question is very easy to do and very quick. So the first thing to do for something like that, it's, we have the expression as x is a function of y is a function of x. It hardly matters. So I'm going to, from this information, first of all, get my dx by dy. That's all I can do, which is easy enough. And if I want it, of course, the other way around, I'll write it and turn it upside down just in case you need it. So dy by dx is 1 over this. I don't know if we need it like this at this stage. Okay, what do we go next? The question is asking for this particular quantity. So how are we going to get the dx by dt out of that? Well, I can continue and say, you know what? Take my dy by dx or dy by dt, hardly matters, and change it into dy by dt. So that's how I normally teach it. Oops. Divide top and bottom of this fraction in speech marks. It's not really a fraction, that's it. But in the limiting, you can't really split it. Let's see what we get for this particular quantity. Well, that is dy by dx, so it's still 1 over, so that's the dy by dx is 1 over 3y squared plus 1. Okay, so we can still leave it in there, it doesn't really matter. So the dy by dt, so when y is equal to 5, the dy by dt, we know it's a quarter, so I can put it in. That's this quantity here. The dx by dt, I want to find at this time. But the y, of course, I know what it is. That's a little bit of space. I could have used this one again. It doesn't really matter which one you're using. I got 1/4 over dx by dt, 25, 75, 76, 1 over 76, multiply across dx by dt is a quarter of 76, which is a ninth. So essentially, dx by dt is in fact 19 in appropriate units. If you assume that the lengths are in something like meters or centimeters, it'll be either meters per second, it's a speed, or centimeters per second or something like that. Units are not really required. How many marks is that? 5 marks. This is a little bit unusual, a little bit different from some of the questions that we see all the time these days in books. It's quite rewarding when you actually achieve it and you manage to do it. Okay, so far so good. I will try to do one more on related rate of change, which is a little bit harder. And for the time being, I'm signing out and I'll be seeing you real soon. Bye bye for now.